In Lab 5, we are investigating the effects of a falling magnet going through a tube of aluminum foil. We will conduct an experimental model as well as a computational model and analyze the differences in the observed and computed time. The physics principles observed and used throughout the lab include Faraday's law, the Boyd-Sverris law, and Newton's second and third law. We will discuss more in depth how they are applied later. Overall in the experiment, we found that the computational model had a travel time of 0.709 seconds, while the average observed time was 2.8 seconds. The experimental procedures are pretty straightforward. We took a tube of aluminum foil and dropped a bar magnet down the center, recording the amount of time in seconds that it took the magnet to travel down the tube. The tube we used for the experiment had a length of 0.3302 meters and a radius of 0.0222 meters, and the thickness of the aluminum on the tube was 0.0127 meters. We repeated the process 5 times, and the raw data can be found on the table to the right, and overall, we got an average of 2.8 seconds. The other component of the lab was to create a simulation of the experiment and to determine a computational model that will also calculate the expected time in the tube. To do this, we started off by defining the physics constants and setting up the initial conditions of the tube and magnet. We will go more in depth into different calculations in a second, but here you can see some of the equations used as well as the simulation results. We can see that the velocity increases downwards for a period of time, then stays constant for a majority of time when it reaches zero acceleration, then continues to increase downwards near the bottom. Then using couple methods and the for loops, I use these to determine the rate of change for the magnetic flux. Find the magnetic field of the bar magnet, the gravitational force on the magnet, and the induced current on each ring. In the next slide, you'll see all the code in more detail. But right now, you can see the formulas used below, as well as the results of the video to the right. Taking a look more directly at the code, after defining the constants and initial conditions, we created a method to calculate the bar magnet's magnetic field using the Boyd-Sverris law. We also created a function that applies the Faraday's law to calculate the rate of change of the magnetic flux, and we calculated the induced current on each ring due to the bar magnet. Next, we calculated the magnetic field on each ring. Using this information and Newton's third and second law, we were able to create the force exerted on the falling magnet. Using our understanding of forces and its relations, this allowed us to display the change in velocity of the magnet over time. In comparison, we found that the computational model had a smaller duration of time in the tube than the experimental model. The computational model is more accurate because there is less room for error. With the results, there are a couple questions to consider. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamic of the falling magnet change? The induced current would be greater, which would result in a larger duration of time that the magnet travels through the tube. On the other hand, what if holes or slots were cut into the tube? How would this affect the ring current in the model? With added holes in the tube, there would be less arbitrary rings and the current would be smaller. And this concludes Lab 5.